Have you ever wondered where everything began? What sparked the creation of the universe as we know it? Our universe is a vast, expansive space filled with countless celestial bodies, galaxies, and mysteries. But it wasn't always this way. To understand the origins of everything, we turn to the widely accepted explanation, the Big Bang Theory. This theory is not a story of a colossal explosion, as the name might suggest, but rather it's a tale of the sudden appearance and rapid expansion of space itself. Let's take a moment to consider the name, the Big Bang. It's a bit misleading, really. When we think of a bang, we think of an explosion, a burst of energy that sends matter flying outwards. But that's not quite what happened here. Instead, the Big Bang Theory suggests that the universe started from an incredibly dense and hot state, and then expanded. It's a bit like baking bread. You start with a small lump of dough, but as it bakes, it expands, growing larger and larger until it's a full-sized loaf. The universe, in this analogy, is like the bread. It started small, incredibly small, and then expanded, growing larger and larger until it became the universe we know today. And just like with bread, it wasn't matter that was flying outwards into empty space. There was no outside for it to fly to. Instead, space itself was expanding. It was the dough rising, the bread baking. Every part of the universe was, and is, moving away from every other part. So the Big Bang Theory takes us back to the very beginning, when the universe was a hot, dense point. And then, for reasons that scientists are still trying to understand, it started to expand, rapidly. So, the Big Bang, it's not an explosion, it's the rapid expansion of space. But how did it all happen? That's the question we'll dive into in our next scene. Until then, remember, we're all just stardust baked in the cosmic oven of the universe. Imagine the universe in its first moments, small, hot, and incredibly dense. It was a soup of raw energy and fundamental particles, packed tightly into a space smaller than the head of a pin. This was a time before time, an era that defies our everyday understanding. As we move forward from this primeval state, the universe starts to swell, and with this rapid expansion, it begins to cool. Imagine a hot cup of tea on a cold day, how it steams and then gradually cools down. That's pretty much what happened, but on a cosmic scale. Now, as the universe expands and cools, something fascinating starts to happen. The energy that filled the universe begins to condense into particles. These particles are the most basic building blocks of matter, things like quarks and electrons. As the universe continues to cool, these particles start to come together, forming protons and neutrons. It's like watching a dance, where the dancers start off separate, and then, as the music slows, they come together to form pairs. Now here's where things really start to get interesting. As the universe cools even further, these protons and neutrons begin to form atoms. This process is known as nucleosynthesis, and it's the birth of atomic matter. The first atoms to form were hydrogen and helium, the lightest elements in the universe. And these weren't just any atoms. These were the atoms that would eventually form stars, galaxies, and planets. So, the universe went from being a hot, dense point of raw energy to a cooler, larger space filled with atoms. It's a bit like watching a loaf of bread rise in the oven, starting off as a small, dense dough and expanding into a larger, lighter loaf. From these humble beginnings, atoms formed, the building blocks of everything we see today. The universe, in its first moments, set the stage for the cosmic drama that continues to unfold, a drama in which we all have a part to play. You might ask, how do we know all this happened? Good question. The Big Bang Theory isn't just a compelling story. It's backed by a wealth of evidence. Let's delve into two key pieces of this cosmic puzzle. First up, we have the redshift of galaxies. In the early 20th century, astronomer Edwin Hubble observed that galaxies are moving away from us, and the further a galaxy is, the faster it's receding. This phenomenon is known as redshift. Think of it like the sound of a siren receding in the distance, becoming lower in pitch. In the case of galaxies, light waves stretch out, moving towards the red end of the spectrum, hence the term redshift. This cosmic redshift is a clear indication of an expanding universe, which is a cornerstone of the Big Bang Theory. The second piece of evidence comes from a faint glow permeating the universe, known as the cosmic microwave background, or CMB for short. In the 1960s, two radio astronomers, Arno Penzias and Robert Wilson, stumbled upon a persistent hum in their radio telescope. They initially thought it was due to pigeon droppings, but after ruling out all earthly sources, they realized they'd detected the afterglow of the Big Bang. The CMB is essentially the oldest light in the universe, a relic from a time just 380,000 years after the Big Bang. It's incredibly uniform, with tiny fluctuations that correspond to slight variations in the early universe's density. These variations eventually led to the formation of galaxies, stars, and everything we see around us. So, when we talk about the Big Bang, we aren't just spinning a tale from thin air. The redshift of galaxies and the cosmic microwave background radiation are tangible, measurable pieces of evidence that support this theory. They're like cosmic breadcrumbs leading us back to our universe's fiery birth. The clues to our cosmic beginning are all around us, even in the glow of the oldest light in the universe. From a universe filled with particles and atoms, how did we get to galaxies and stars? This is the big question as we delve into the formation of these celestial bodies. In the aftermath of the Big Bang, the universe was a hot, dense sea of particles and atoms. As the universe cooled and expanded, these particles began to coalesce, forming the first atoms of hydrogen and helium, the simplest and lightest elements. But these atoms didn't just sit around. They were drawn together by one of the fundamental forces of nature, gravity. Now, imagine a vast, almost infinite cloud of these atoms floating in space. Over time, gravity pulls these atoms closer and closer together, forming dense pockets of gas. These pockets become so dense and so hot that the pressure ignites a nuclear reaction at their core. This reaction emits light and heat, and just like that, a star is born. The same force, gravity, also leads to the formation of galaxies. While stars are forming, gravity is also pulling groups of them together. These groups of stars eventually coalesce into galaxies, each with billions or even trillions of stars. But this process doesn't happen overnight. It takes billions of years for galaxies to form and evolve. And the most astounding part? This process is still happening today. Across the universe, clouds of gas are collapsing under gravity's relentless pull, igniting to form new stars. These stars will eventually gather into galaxies, adding to the universe's ever-growing family of celestial bodies. So next time you gaze up at the night sky, remember the cosmic journey each star has taken. From a sea of particles to a glowing beacon in the sky, each star is a testament to the universe's ongoing evolution. In the vast cosmic dance, galaxies and stars continue to form, a testament to the universe's ongoing evolution. The Big Bang Theory provides a compelling picture of our universe's birth, but it also leaves us with intriguing questions. Some of these questions make for heady dinner conversation, while others keep astrophysicists awake at night. Let's delve into the first conundrum. What caused the Big Bang? The theory itself does an excellent job of explaining the aftermath, but it remains silent on the actual cause. The question of what set off this colossal explosion, triggering the birth of the universe, remains a tantalizing puzzle. Then we have the question of what happened before the Big Bang. If the Big Bang was the beginning of time and space as we know it, then what existed before it? Was there a different universe, or perhaps an endless cycle of universes? It's a mind-bending concept that challenges our understanding of reality. And what about the future of our universe? If it continues to expand, as current evidence suggests, will it go on indefinitely? Or will there be a point when the expansion slows, stops, and perhaps reverses, leading to a big crunch? It's like trying to predict the end of a story that's still being written. And let's not forget the mystery of dark matter and dark energy. They make up a staggering 95% of the universe, yet we know virtually nothing about them. They're like the shadowy figures lurking in the background of our cosmic story, influencing the plot, yet remaining unseen and unknown. These questions remind us that science is a journey, not a destination. Each answer we find only leads to more questions, driving us to explore, investigate, and understand. The universe is like an intricately woven tapestry. The more closely we look, the more intricate the patterns become. As we continue to explore the cosmos, perhaps one day we'll uncover the answers to these cosmic mysteries, further illuminating our understanding of this place we call home, the universe.